Welcome to Earth Science 10. I'm Holly, your professor. The textbook for this class, it is important. You do need to do the reading. What we do to help you save money is we allow you to use any of the last three editions. There's really very minor changes between the different editions in the book. And I do include the reading, the specific reading for each of the three editions. So, go online, see some students get copies of the book, 2 editions ago or 3 editions ago for $5. So do that. It's really worth your time because you don't have as much interaction with me as you would with a face-to-face class. Now, Earth Science, some students think it's an easy class, and it's really not an easy class. This is 4 classes rolled into one. Let's say that you love astronomy. You may feel kind of ripped off. I don't spend a lot of time talking about astronomy. It's just one section of this class. So the 4 classes that I'm basically going to cover are astronomy, geology, oceanography, and meteorology, all of which are full semester courses at Sierra College. So if you find that you really like one of these topics, go ahead and take one of the classes. I'll give you a good introduction, but you really ought to take a full class in this. So it's not easy. We do cover it a little bit more lightly than those, obviously the 4 different classes would. And what Earth Science does is it's not all about rocks. It's about studying Earth and all of Earth's neighbors in space. This slide is just a reminder that there are a lot of other educational tools that are included in each of these weekly folders, and including some of them are audio pods, other little audio lectures. Some are visual enhancements. So whenever you see one of these, make sure that you also go find the other lecture that goes with it. Now, we need to start at the beginning, and the beginning of space, time, and the universe is basically explained by the Big Bang Theory. I know in that other audio section I have a little bit about theory versus hypothesis, the scientific method. You definitely want to go listen to that. And the Big Bang about 15 billion years ago. Now you guys, you're going to come across 14.6, 14.7 billion years. It's all close enough. So about 15 billion years ago, there was a massive explosion, and that basically created time, space, and matter. The explosion, energy was formed, and energy transforms over into matter. E equals mc squared. I think all of you guys recognize that formula. Energy equals mass times the speed of light squared. Over time, the energy changed over into matter, and eventually that will lead to our solar system and you and I. So the Big Bang Theory states that we had a single point origin for our universe, and then after this massive explosion, everything is moving out and away from that single point. And we're going to see that that's actually going to be a piece of evidence that is pretty easy to understand. Now, the last bullet in there, the fate of the universe, when I was a student, they didn't know much about this, and they weren't sure if the universe would just kind of continue to open up and just kind of slow down and lose energy and then stop moving. But there was actually a school of scientists, or a group of scientists, that believed that eventually the energy would decrease enough, and then the mass of the matter that was made would start to be attracted to each other and would actually come back together. And it's kind of called the crash and bang theory, where it opens up in a bang and then it comes back together in a crash and then would maybe open up again in a bang. And unfortunately, I think that's been disproved. They do believe that eventually the universe will stop opening, but it won't come back in together. Now, a piece of evidence that I have actually witnessed myself that helps to support an opening up an expanding universe and helps to support the Big Bang Theory is this thing called the redshift or the Doppler effect. Most of us know about Doppler effect because we know about Doppler radar. If you watch the weather channel or the weather reporter on the news station, they oftentimes show Doppler radar to kind of map where the rainstorms are and things like that. And Dr. Doppler was a very famous physicist who this effect is named after. Now, light travels as waves, as does sound, and you actually experience the Doppler effect pretty much every day as it pertains to sound. Think about it. When you've been standing on the sidewalk and you hear a siren, typically you can tell if the siren is coming closer to you or if it's moving away from you, and you can tell that by the pitch. Make sure you look at the animation that I've included in here that has the police car passing you by. When the police car is approaching you, the pitch is high. When the police car passes by you, the pitch lowers. Sound, when it's high pitched, is shorter wavelength. When sound is lower pitched, it's got a longer wavelength. So waves of energy as they approach you are shortened, and their wavelengths are shortened. And when they move away from you, the wavelengths lengthen. And in sound, that would be high-pitched as it comes towards you and low-pitched as it moves away from you. Now, since light is also a wave, just as this worked for sound, it also works for light. When light energy approaches you, its wavelength is shortened, and this is the blue part of the electromagnetic spectrum. When the light passes you by and now is moving away from you, the wavelengths lengthen or increase in wavelength, and that is now the red, called the redshift, or the red part of the electromagnetic spectrum. Blue is shorter wavelength, red is longer wavelength. So when you look at distant space objects through special telescopes, what you see is that all of those distant space objects outside of our solar system are all moving away. Okay, and what that helps to support is a single point origin. We had a massive explosion and everything moves outwards. Now imagine your surprise if you're looking through your special telescope at distant space objects and, oh my goodness, they're blue shifted. Okay, what that would mean is that everything is now coming back towards you, and that really wouldn't be very comforting. Just a couple pictures to kind of help you understand this. Here is a bread dough that has yeast in it, and it's rising, and over time each of the objects becomes farther and farther away from each other, and that's what's happening. Our universe is expanding out in all directions, and so all objects are becoming farther and farther away from each other. All right, galaxies. So we have our universe, and within our universe there's hundreds of millions, or hundreds of billions even, of other galaxies. Remember, our galaxy is called the Milky Way galaxy. But we're just one of many hundreds of billions of other galaxies. And in fact, with just a simple 8-inch telescope, you can see many of the other galaxies that are visible here from our galaxy or from Earth. And in fact, you can actually see part of our galaxy, the Milky Way galaxy, on a clear night when you go out and you look, up into the sky. You can see something that looks like very, very high wispy clouds, and you're actually looking through part of the Milky Way galaxy. Now, our galaxy is a spiral galaxy, and I'm not going to test you on the different types of galaxies, but you should kind of know, that we are in the Milky Way galaxy. Light years, this is kind of important. Once we get outside of our solar system, we measure things in what we call light years, and if you are a science fiction fan, this is no new measurement to you. A light year is the distance that light travels in 1 year, and it's a pretty big distance. So our galaxy is about 100,000 light years wide. It kind of looks like a fried egg. Wait till I show you guys the pictures. It's pretty easy. It's only about 10,000 light years thick, and that would be kind of the yolk part of a fried egg. Now, we're not a beautiful, perfectly symmetrical spiral galaxy. We have two beautiful arms, and we actually have this kind of third mutant smaller arm, and I'll show you guys. Again, pictures are worth 1,000 words. Here is a diagram of our galaxy, and you can see it's about 100,000 light years wide, meaning it's pretty darn big. In the center we have the nucleus. You can see the two pretty nice looking arms, and then that third arm, that's what I call the mutant arm, but it's perfectly acceptable. And remember, our solar system is not the center of our galaxy, and our galaxy is not the center of the universe. You can see the arrow that's pointing where it says Earth Sun, or that's the Earth Sun, and so we're just on one of those little arms. Okay, here is a cross-sectional view of our galaxy, and what you can see is, remember the fried egg analogy. The thicker nucleus, it's about, 10,000 light years across, thickness-wise, and then you guys can see in length it's 100,000 light years across. All right, kind of interesting. If you study philosophy, you have come across the name Immanuel Kant. And what he was actually, back in the olden days, you had wealthy people that didn't have to worry about feeding themselves, putting a roof over their heads and things like that. And a lot of them actually pursued academics. And so they were what we call Renaissance men. And they were very well versed in many different subjects. And not only was he an excellent philosopher, he was also a closet astronomer. And he's actually the first one to come up with the ideas that we have other galaxies and that they come in a number of different shapes. We've already seen a picture of the spiral galaxy, and besides the Milky Way galaxy, there's many spiral galaxies. We have elliptical galaxies, we have barred spiral galaxies, and we also have irregular galaxies. And I'll show you guys a few slides. Okay, so here we have the Great Galaxy, which is also a spiral galaxy. I think you guys would really be surprised that with just a simple, couple $100 telescope, you can go out and see other galaxies, including this one. Okay, this is a barred spiral. Notice it's a spiral, but it's got very straight arms coming out right from the nucleus. Kind of looks like something out of Star Wars. So that's a barred spiral galaxy. I don't believe I have a picture of an elliptical or an irregular, but my favorite irregular one looks like a donut with a hole in the middle. And they think the hole in the middle came about from another galaxy passing right through the center and punching it through. All right, here's a slide just talking a little bit about distance. We're going to be talking about our solar system coming up here. And when we talk about, how far away is the moon and how far away is Mars, a lot of times we just talk about miles here in the United States. Remember, we use miles. But in Europe, you might talk about how many kilometers. I think the moon is something like 180,000 miles away from the Earth. But once you get outside of our solar system, we don't use miles. It gets too large, and scientists are basically lazy. We use light years, and again, the distance that light travels in 1 year, and light's pretty darn quick, so that's about 5.8 trillion miles is how far light travels in a year. Kind of something that's surprising. Some of these distant stars that we see, they could have burned out many thousands of years ago, and we wouldn't know because the light is still traveling to us. In fact, our sun could burn out, and for 8 minutes we wouldn't know because of the distance between the Earth and the sun. So light year is just kind of an interesting thing, but this is what we use to measure objects outside of our solar system. Now, the closest star to us, other than our own star, the Sun, is Alpha Centauri, and it's 4.3 light years away. Okay, 4.3, that's a pretty easy number. Look how many trillions of miles. And in fact, if I made you put all the zeros behind that, that would be a crazy number. Scientists are lazy, and you guys are going to see that throughout this entire class, that we're going to have a lot of shortcuts to make the numbers easier. That just means less math problems and less math mistakes. All right, this is important, the STD question. What controls how bright a star is? And brightness, kind of a fancy word for it, is magnitude. You guys know when you go out at night and look up at the stars, some of them are very bright and some of them are not so bright. There's 3 different things. The size of the star, is it large, medium, or small? The temperature, is it hot, medium, or cool? And the distance, how far from Earth, which is our point of view, is that star? Now, the brightest star in our galaxy, we may not even see it because it's so far away. So remember, we're stuck here on Earth, and so this is our perspective. So we pretty much use distance from Earth. Now, don't stress about details. It's all about relative, hot, medium, cool. So don't, Kelvin is another measurement that chemists and astronomers use. It's even hotter than you think it is if you know a little bit about Celsius. But hot stars are really, really hot. And hot stars are huge stars. And they actually look blue. So when you look out at the sky, if you know where Orion is, when Orion comes up high enough, behind it is Sirius, or the dog star. And it's a bright blue star. And that's a very large star, and it's a very hot star. All right, the sun, everyone's seen the sun. Don't look at it too closely. It's a yellow star, And it is actually a very average star. It's average or medium in size. It's medium in temperature. Okay, and it appears yellow. Now, cool stars appear red. Back to Orion. Everybody knows Orion. When Orion comes up, you know where Orion's belt is. Look up. Look at his armpit. It's a giant red star called Betelgeuse. But in fact, it's not a giant star. It's just it's closer to Earth. And so it looks really big, but it's actually a small star, and it's actually a relatively cool star. Now, when I say cool, I don't mean cool like you can go walk on it. It would fry you in a second, but it relative to a blue star or a yellow star, this is a cool star. Okay, and it's small in size. All right, now this is kind of a surprise to most people. Most stars are twin stars, and you might say, well, the sun doesn't have a twin, and you're correct, but it almost did. If Jupiter had been 10 times as big, we would have two stars in our solar system. So binary stars, more than half of all stars actually are twin stars, or there are two stars within one solar system. Now, even if we can't see the second star, you know, with using a telescope, if we can't see it, we could tell it was there mathematically. I'm not going to ask you guys a question about this on the test, but it's actually pretty interesting. If you are interested in this, come in and talk to me in office hours. I'll explain it to you. It's pretty cool. Now, this is kind of neat. If you guys look in your book, you will see a diagram about the life of a star. A star is born, a star reaches adulthood, and then a star basically dies. And sometimes a star dies pretty spectacularly, like a red supergiant or something. But a star is born, and it goes through an ugly, awkward stage where it's not in balance. And what has to happen for our star to become what's called a main sequence star or an adult star is that the two forces working against each other have to become equal or get into equilibrium. And gravity is what pulls the material together, and thermonuclear energy is what causes the star to expand. And so when those two forces equalize or go into equilibrium, then that star is now an adult star, and our sun is an adult star, or a main sequence star. Now, don't worry about this for the exam. I think all of us have gone outside and like I said, Orion. I bet everybody knows Orion. And so these are constellations, and these are very Eurocentric. Europeans, Americans, we've named these after Greek and Roman mythological characters and things like that. But if you guys go to China, inland China, and you talk to, you know, people, native people there, they have their own stories, and you know, anywhere you go, they have their own stories and their own figures that they see up in the stars. So it's just a way that we kind of split up the night sky and kind of learn our geography of the night sky. It's like saying, oh yeah, take a right at that, you know, bright pink mailbox or something. But I like it, it's interesting, and it's pretty useful. Now, if you go to the southern hemisphere, remember, you're going to see very different stars. You won't be seeing Orion in the sky. Now, this is important. Our sun. We talked about it before. It's a very average star. It, you know, it's average size, average temperature. It's also going to have an average lifespan. It'll have a lifespan of about 5 billion more years. So it's been around for 5 billion. We're going to talk about that. And it'll last for another 5 billion. So it'll have a total lifespan of about 10 billion years. Again, it's just one of, you know, many hundreds of billions of stars within the Milky Way galaxy. And remember, we're just one of many hundreds of millions or billions of galaxies within our universe. It is the only star that's close enough that we can actually study its surface, but please don't try to study its surface. Astronomers have special filters. If you look at the sun, you'll burn your eyes. It'll burn out your retinas or something. So don't do that. They have special tools to do that. And you know, if you look on YouTube, look at some of the videos. They're pretty spectacular. All right, I do have another lecture up here about the sun. It is pretty important. It's about the different layers of the sun, which there are 4 different layers of the sun. 2 are the main body of the sun, 2 are atmospheric, and you guys will have an in-class assignment, and it will be a test question. You need to know these. And what I want to know is one of the kind of specific information about each of these layers, saying, it's the first layer, the second layer, the third layer, the fourth layer. That's not good enough. The solar interior is the nuclear powerhouse. It's where nuclear fusion happens and the energy is created. We actually can't see this. Okay, I do have pictures, I've got diagrams, so you can kind of look through this and make sure you kind of understand the 4 different layers. Okay, the next layer up, which is actually the surface of the sun, is the photosphere. It's the sphere of light. Now, wait till I show you the picture. It's got kind of a granular looking surface, and that's because of something called convection. When material heats up, it expands. When it expands, it rises. When it gets away from its heat source, it cools, it contracts, it becomes more dense, and it sinks. And so these blobs that you see are part of that convection. And you guys, convection, this is going to be on every exam. We're going to talk about convection in the sun, convection in the earth, and finally, convection in the atmosphere. And don't forget density. Less dense things rise, more dense things sink. All right, here is a shot of the photosphere, and you can see those granules, and those blobs are part of the material that rises up because it's less dense, and then it cools, it condenses, and it's going to sink because it's more dense. Okay, the first layer of the atmosphere is the chromosphere, and what's really kind of important and unique about this layer is those spicules. Imagine going into a chemistry lab and lining up all of the Bunsen burners and turning on the gas and lighting them all up and just having all of them lit. That's sort of like the surface of the chromosphere. It's like a bunch of hot incandescent jets of gas that are burning. And I'll show you guys both pictures and diagrams of this. Okay, you can see actually the red spikes that are labeled spicules. It's going to kind of look like an angry cat. When your cat gets mad, its hair stands on end. You can also see these during a complete solar eclipse. You can actually, be careful about looking at the sun. If you are in an area with a complete solar eclipse and there's an astronomer that says it's okay, you can actually see these. And I'll show you guys what it looks like. It really looks like a mad cat. And here's the actual picture. So see the hair that sticks up on the sides of the sun there, and that is the chromospheres or the spicules. All right, the outermost layer is the corona, Spanish for crown. Now, I don't like that word unstable. It should say tenuous or dynamic. It's kind of like a ghost. If I was to put a little animation of a ghost, I'd have it wiggling and moving around and things like that. This is a layer that's in motion. Now, this is the hottest layer of the sun. And it's a pretty important layer. It is where the solar winds are produced and the solar winds escape. Now, the solar winds never have a star by it. They would like to fry you, but luckily the Earth has a layer that helps save us from being fried, and that's actually the Earth's magnetic sphere. It's like a shield. It's kind of like a superhero. Now, everybody's probably seen a picture of the northern lights or the southern lights, the aurora borealis or the aurora australis, and that's actually the Earth's magnetic sphere battling with those solar winds. So the hottest layer and the source of the solar winds. Okay, and here it is, and if this was an animation, it would, the outermost part there would be wiggling around like a ghost. Now, we are going to be talking mostly in the last section of this class about the energy from the sun. The sun puts out a lot of energy. It is the main source of energy for the Earth, and we'll talk about the inside energy of the Earth and the external energy of the Earth. We call this the electromagnetic spectrum, and it actually, there's a lot of different energy that comes off the sun. Some of it, we'll start with some pretty low wavelength. Gamma rays. Now, you probably know gamma rays because that's what made the Incredible Hulk, right? X-rays, okay? And we got to protect ourselves against X-rays. If you become an X-ray technician, you're going to be standing behind a lead curtain a lot to make sure you don't get a lot of X-rays. So luckily, it's not mostly X-rays coming off of the sun. Ultraviolet light. This is another thing we're going to be talking about. This is something you don't want a lot of this touching your body. This is what gives you skin cancer. This is what gives you cataracts, makes you blind. And another layer of our atmosphere actually helps protect us, and that's called the ozone. And we're going to talk about the ozone layer up in the top of the stratosphere in our last section. Phew. The main source of energy coming off of the sun is visible light. Okay, and this is white light, and if you take a prism, you separate it out into the colors of the rainbow. And so all of those different colors of the rainbow together make up the visible light spectrum. Now, you and I see in the visible light spectrum because we evolved, and this is the main, here on Earth, and this is the main energy coming off of the sun, our external heat source, and that's why. Now, infrared, the sun does put off some infrared. We're going to also talk about this. The Earth puts off infrared energy. This is if you eat at a cheap hamburger place, they cook a bunch of hamburgers, they stick them under heat lamps, that's infrared heat. It's a heat lamp, sort of. All right, and then the last thing that the sun puts off, radio waves. You guys can tune in to the sun. It's not pretty. It sounds like something, somebody stepping on cat's tails. It's not rhythmic or anything, but the sun does put off radio waves. So these are the different parts of the Earth's electromagnetic spectrum, and this will become pretty important in that last section, so on our third exam.